Welcome friends, in this video we are going to look at the science paper 2 for the year 2023. And this paper was written by the external candidates. Now we are going to begin with question 6 here. Define the term more. What is meant by a more? Now how I like to look at what a more is, I think of this as a dozen. Remember, 1 dozen simply means 12 items. If I say I have 1 dozen of eggs, it means I have 12 eggs. So a dozen simply means it's a fixed amount. It can represent anything. If I say I have a dozen of mathematical sets, it means I have 12 mathematical sets. Now, how can we compare a dozen to a more? A more also simply means a fixed amount of certain substance that we are going to look at here. Let's say, for example, if I say I have a more of calculators, this means that I have calculators of about 6.02 times 10 to the power 23. Now, the only difference that we can see between a dozen and a more is that a more is a very large number. It represents billions and billions of stuff. Now, if we say we have a more of sodium atoms, it means in that 1 mole of sodium atoms, they are 6.02 times 10 to the power 23. So we can simplify or say that a mole represents a number which is 6.02 times 10 to the power 23 of items. It can be ions, it can be molecules or particles. Now let's have the definition for what is really meant by a mole. So the more can be defined in so many ways, but we are going to use some simpler languages here. We'll say this is the amount of substance containing the same number of molecules of, it can be atoms, ions, or radicals as compared in 12 grams of carbon. So we always compare this to 12 grams of carbon. So that's what it means by a mole of a substance. Now let's have question B. The concentration of sodium hydroxide solution is 0.25 mole per decimeter cubed. So we are given concentration. Calculate the number of moles of 0.25 mole per cubic decimeter of sodium hydroxide solution contained in 250 cubic centimeter of this solution. Now there are so many formulae that we can use to find the mole, but what determines the actual formula that we can use is the data that we have. For example, we are dealing with a question where we are given the concentration. So the question is, how can we find the number of moles given the concentration and the volume? Let's look at some formulae that we can use. So the first one, we have number of moles is equal to mass over molar mass. So this one, you only use this one if you are given mass. Whenever the question states or says the mass of a substance is this, calculate the number of moles. This is the actual formula that you are supposed to use. The second one, we can also find the number of moles if given the number of particles. X can represent the number of particles, ions, or molecules. over Avogadro's constant. So the Avogadro's constant is the number that we looked at earlier, which is 6.02 times 10 to the power 23. So this number is a constant number. It's a number that you're supposed to know. You may not be given in the question paper, so they can consider that you know this number. So what I can advise is that make sure you commit this number to memory. It's very important. The third formula that we can use to find the number of moles is this one, where we are given the volume of a gas divided by the molar volume. So for molar volume, if the question says under STP, the molar volume is 22.4 decimeter cubed. That is the number you need to substitute with Vm. While if it states RTP, room temperature and pressure, the molar volume is given by 24 decimeter cubed. Remember, this formula can only be used to find the volume of a gas. You can't, the number of moles of a gas. You can't use this formula to find the number of moles maybe of a solution or maybe a solid. It's only a gas like carbon dioxide, oxygen is when you use this formula. The fourth formula that we can use to find the number of moles is this one. Number of moles is equal to concentration times volume. Now, from these four formulae, which formula is applicable according to the data? So let's look at what we have. We have the concentration of the solution and also the volume of the solution. Since we have the concentration and the volume of the solution, the formula that we are going to use is this one. So this is what you are supposed to do. You need to know or master this formula. Then from there, the data that you are going to be given according to the question will help you to choose the correct formula that will give you the actual answer. We can now write the formula. Number of moles is equal to concentration times volume. Make sure that as you are calculating number of moles given the concentration, make sure that the volume is in cubic decimeters. But to this question, the volume is given to centimeter cube. So what are we supposed to do? We need to convert these 250 cubic centimeters in decimeter cubed. We are going to use this conversion factor, which says 1 decimeter cubed is equivalent to 1,000 decimeters, centimeters cubed. If we are converting from decimeters into centimeters cubed, multiply by 1,000. The reverse is also true, where you divide. So from centimeter cubed to decimeter cubed, it's division. You need to divide by 1,000. The volume that you are given, make sure you divide by 1,000. Now we can show our working. We know that 1 decimeter cubed is equal to 1,000 centimeter cubed. Since the volume is given in centimeter cubed, our centimeter cubed will be written on the right side here, so that we may have the same centimeter cubed. We put x, we cross multiply. I'm just showing the work. The key point is you divide by 1,000. So 1,000 times x is 1,000 cubic centimeters x. 250 cubic centimeters times 1 decimeter cubic centimeters is 250 cubic centimeters decimeter cubed. You divide by 1,000 centimeters cubed, 1,000 centimeters cubed. Centimeter cubed cancels, 0 we cancel. 25 divided by 100 is 0.25 decimeter cubed. To make it simple, if you are converting from centimeter cubed to decimeter cubed, divide by 1,000. We can now go back to our formula. Number of moles is equal to concentration is this number 0.25 mole per decimeter cubed times the volume is 0.25 decimeter cubed, which is, we can cancel this. If you go on the calculator, 0.25 times 0.25, so I'm getting 0.0625 moles. These were the moles of sodium hydroxide. So this is what we can do whenever you are trying to find the number of moles given the concentration. So what you just have to remember here is that make sure that the volume is decimeter cubed, then the concentration, you can tell, should be in mole per decimeter cubed, or sometimes you may just be given molarity. You may see the number like 0.25. Whenever you see a capital letter M, just know that it's still concentration. Now we move on to question C. Iron metal is extracted from an iron ore called hematite in a blast furnace during a reduction reaction during using carbon monoxide gas as a reducing agent, as shown in the following chemical equation. We have been given a balanced chemical equation, and this equation summarizes the reduction of iron ore from the iron 3 oxide to iron. Now let's not focus on that. Our task is calculate the mass of carbon monoxide. We want the mass of carbon monoxide gas required to reduce 3,200 kilograms of iron 3 oxide in the blast furnace. Let's go to our balanced chemical equation. If the equation was not given, if you encounter a question where the equation is not given, first begin by writing a balanced chemical equation. They were lucky because they were given a balanced chemical equation. Their task was just to start making calculations. Now, your focus is, first you need to look at, there will be one substance whose mass will be given. And from this question, we can see that iron 3 oxide, the mass is given, which is 3,200 kg. Let me put letter X here. So this X is there to show me that the substance has the mass. Then number 2, from the remaining substances, I'm going to put a Y on the substance whose mass we are calculating. So your focus should be on the substance whose mass is given and the substance whose mass you are looking for. We are calculating the mass of carbon monoxide. So on the carbon monoxide, I put Y. So my focus, the reason why I have indicated X and Y, you can use in later. The reason why I have indicated X and Y is to help me that this is my focus. So I'm going to focus on only these two, because one of these, the mass is given, the other one is the substance whose mass we are looking for. I will write them down here. I can ignore the coefficient for now. What is the mass of iron 3 oxide? Is 3,200 kilograms. Now let me make a statement here. You can, whenever you are calculating, you are given mass and you want to use that mass to find mass, you can calculate the mass whether in grams, you can use it in grams, or you can use it in kilograms. The only exception that we have here is that you can only use, you are supposed to use mass in grams if you are calculating the number of moles using this formula. Whenever you are using this formula, the mass should always be in grams. Let's go back to this one. Our mass for iron 3 oxide is 3,000 200 kg. For carbon monoxide, we don't have. Let's just put X. This X is there to represent the mass that we are solving for. Step 1. Step 2, we are going to find the relative formula mass for iron 3 oxide. Let's begin. So say Mr. iron times the number of atoms of iron is 2 plus oxygen times 3. Iron, if you go on the periodic table, iron has the mass number of 56 times 2 plus 16 times 3. 56 times 2 is 112. 16 times 3 will give us 48. The sum of 112 and 48 is 160. Now remember here, the mole ratio is 1. So even if we multiply 1 times 160, we still get 160. So this 160 will be here. You put 160 here. Then we need to find also the relative molecular mass for carbon monoxide. Carbon monoxide, we can see there is only one, also one. One atom of carbon plus one atom of oxygen. The mass number for carbon is 12 times 1 plus 16 times 1. 12 plus 16. The sum is 28. 28 is the molecular mass. 28 is the relative molecular mass for one molecule of carbon monoxide. One molecule of carbon monoxide has 28. Now because we have a 3 here, it means we have 3 of these. So this means that there is 28 plus another 28 plus another 28. Or to summarize and simplify this, we just have to multiply this by the mole ratio, which is 3. 28 times 3 is 84, is what we are going to put here. We cross multiply. 160 times x is 160. X is equal to 3,200 multiplied by 84. I'm getting 268,800 divided by 160. The mass is 1,680. Since the mass that we are using is in kilograms, even the answer will be in kilograms. So this is how we can calculate the answer for this one. Let's move on to question 7a. Describe how the action of heat on the carbonate of a metal depends on the position of the metal in the reactivity series. We are looking at decomposition. For example, if we have calcium carbonate when heated decomposes to form calcium oxide plus carbon dioxide. Take note of the metal that is under the carbonate here is calcium. Calcium is in group 2. Let's say we have sodium carbonate or potassium carbonate. What happens if sodium carbonate or potassium carbonate is heated? Sodium carbonate or potassium carbonate will not decompose when heated. Why? Because the metal that is in that particular carbonate is more reactive. So the most reactive metal, or the carbonates of the most reactive metal, does not decompose when heated. That's a point. That's why we have to put into consideration the reactivity series for these metals as we are solving for decomposition. So the more the reactivity is increasing, then in terms of decomposition, then it is reducing. Some may decompose partially, but most of the reactive metal forms a very stable carbonate. So that is what we are looking at here. Now let's go back to our question. The question is, describe how the action of heat on we'll say the most reactive metals forms a very stable carbonate which does not decompose when heated. Now, as you are studying, you're going through this, I can advise you do not try to master these the way they are. The key is for you to just have to get the concept. There are so many ways in which you can answer this same question. The key is, as long as the key points are there. The key points are that the most reactive metals form very stable. They are very stable, such that they do not decompose. If they were to decompose, they can only decompose partially. So that's the information that you are supposed to have. Or we can say the decomposition of metal carbonate depends on the position or how reactive the metal is, because the carbonates of most reactive metal will not decompose. For example, you can give sodium carbonate, potassium carbonate. Why? Sodium and potassium are from group 1, and we know that from group 1 periodic table are metals that are very reactive. Let's move on to question B. Transition metals and their compounds can be used as catalysts. Explain what is meant by the term catalyst. Is a substance that can alter or change the speed of a chemical reaction without itself being used. This is one of the definitions. You can also write the definition that you know. Then for question 2, explain why metals are good conductors of electricity and heat. Metals are good conductors due to the presence of delocalized electrons. If you look at the delocalized electrons, these are electrons that are free to move. Okay, so we can say these are electrons that are free to move. The summary that we can look at in terms of conductivity of electricity and heat is all about the movement of electrons. That's why from the word electricity we have electro. So this one comes from the word electron. So electricity is just the movement of electrons from one position to another position in a conductor. That's what we can summarize. We move on to question 8. Greenhouse gases are given greenhouse factor values. The greenhouse effect of a gas increases with the factor value. The following table 8.1 gives information on 4 different gases. Here we are looking at the effect of greenhouse factors toward the climate. That's why we have the climate change. The first one, we have carbon dioxide, greenhouse factor 1, percentage of gas in the atmosphere 0.036. The second one, methane 30, 0.0017. The nitrogen oxide 160, 3 times 10 to the power negative 4. This is same as 0.0004. For this one, for the fourth one, carbon trichlorofluoride would be 0.000000028. We can see the numbers. The largest is this number, the first one, then followed by the way, okay, so we can just say the way they were listed is according to their descending order. We began by the largest, then up to the least number. Question A, identify the gas which has the greatest effect on the environment. Give a reason for your answer. If we are to give, depending on the greenhouse factor, the carbon trichlorofluoride can be this one, but in terms of the occupation of the gas in the atmosphere, the percentage is so small. So this one is so very small in terms of the percentage occupation. Now if you look at carbon dioxide, the greenhouse factor is very small, but the occupation is big. So the answer is carbon dioxide. Even if the greenhouse factor is 1, it occupies the largest in terms of the amount in the atmosphere. So that's our answer there. This is because carbon dioxide occupies a large portion of greenhouse gases. Okay, we move on to question B. Why is an increase in the percentage of methane more worrying than the same percentage in the increase of carbon dioxide? The reason behind this, we can say, the first one, methane is a dead fuel. Dead fuel, it means that it pollutes the environment. Then also during the complete combustion of methane, we are going to get carbon dioxide. So the carbon dioxide can also be produced by methane during the complete combustion. Then the other thing is methane is a dead fuel. Methane is a dead fuel which produces carbon dioxide during complete combustion. That's the reason why the increase of percentage of methane is more worrying. Okay, because of this. We have question C. What other environmental problem besides its action as a greenhouse is caused by carbon trichlorofluoride. So the other, apart from greenhouse, is that this one can change the rain pattern. The CC3F can change the rain pattern. Rain pattern is where there are months where we expect to have rain, and imagine in those times we may have droughts, so that may be an issue. So this one can change the rain pattern. Apart from the rain pattern, it can also bring diseases. So there are so many. These are some of what that we can look for here. Okay, question 9, the last one. You can pardon me with the paper, it's not that clear, but let's see what we can get from this. Alkanes, the one ends with ANE, form a homologous series of organic compounds which are also called paraffin. Roman number 1, state the general molecular formula to which the alkanes conform. It's CN H2N plus C2. That's a formula for all alkanes. Then the second one, draw the displayed structural formula of pentane. So from the word pentane, we can divide it. We have the first one, pent. So before we look at that, first let's look at what we call prefix. Prefix, the first one is meth, where you have 1 carbon, eth, 2 carbons, prop, 3 carbons, but, 4 carbons, pent, 5, hex, 6, hept, 7, oct, 8, non, 9, dec, we have 10. These can help you to remember, and these are known as the prefix. So the prefix tells you the number of carbons that you have. Then for the suffix, changes depends on the homologous series that you are looking at. Whenever we are looking at the alkanes, the suffix is ANE, or whenever you see ANE, it is an indication that you are dealing with alkanes. It's a family of alkanes. There are certain things that you need to know about alkanes in terms of the bond. They contains the single bond. Now, after we know this one, let's go back to first we need to come up with a molecular formula. So first look at the prefix, which is pent. Pent is 5, so we need to go back to the chemical formula. So CN H2N plus 2. Where there is N, since pent is equal to 5 carbons, where there is N, we put 5. We can now do the mathematics. C times 5 is C5. 2 times 5, 10 plus 2, 12. This is the molecular formula for pentane. Now, since we are told to write the displayed structure formula, we first begin by writing the 5 carbons that we have. Remember, the suffix is ANA. So what does the ANE indicate? ANE indicates that we need to have the single bonds between all carbons, not double bonds, will be here. So here we put the single bond, here, here, here. Then from there you show the hydrogen. So you put the hydrogens here. This is our structural formula of pentane. And if you want more of these organic, I have created videos on organic chemistry. You can just search you'll be able to find more of these so that you may have the full information. Then question B, give 2 reasons why cracking of large hydrocarbon is important. The first one, to form smaller fractions to meet the demand. The second one, to form alkenes. So cracking is one of the process that can help us to give us the alkenes. The last one, justify why alkenes are sometimes called paraffins. So the reason is because they are saturated. Saturated means they have single bonds. Or we can say that for this to react, we need to at least have some drastic conditions that should be met. So that's it for this video. Thanks for watching.